Hi everyone. Today we're starting on the last lesson for the module. We're going to be learning about some of the consequences of special relativity as they apply to the real world. In particular, we're going to be looking at the twin paradox, some of the evidence for special relativity, and finally at some of the consequences that this will have for future space travel, especially space travel at very fast speeds. So, to begin with, we'll be talking about the twin paradox. Now, the twin paradox is an interesting paradox that arises from the laws of special relativity. A paradox, by definition, is a way of getting two different results from the same set of rules. And so if there's a paradox in a set of rules, then if there's no solution, the set of rules can't be correct. So, let's see what the twin paradox is and how we solve it. Now, as you know, relativity is a little bit odd, right? It's very, very different to all the physics we've been learning before. One of the consequences is that space and time aren't fixed quantities, for example. And this means that to all the physicists who were around when Einstein discovered it, it seemed absolutely absurd. And so, they tried to come up with paradoxes that would find flaws in Einstein's theory of relativity. They applied the laws in two different ways, in such a way that the results of applying it one way were different to the results of applying it another way. And of course, when a paradox happens, it means that there's something wrong with the rules, or that you've overlooked something during your construction of the paradox. One of the most famous paradoxes that Einstein's contemporaries came up with is known as the twin paradox. Let's take a look at it. Suppose we have two twins living on Earth. Here we have Barnard and Gaia. So one twin, Barnard, decides to go to Barnard's star, which is a few light years away from our Sun. And he goes with a very fast-moving spaceship, which means it will be able to take into account the effects of special relativity. The other twin, Gaia, will stay at home. Now, how does time pass from each twin's point of view? Well, using the laws of special relativity and time dilation in particular, if we look at Gaia's rest frame, then Gaia ages as normal. As far as she can tell, time is passing normally. But when she looks inside the fast rocket ship that her brother Barnard is in, time passes slowly inside that fast-moving ship. Because inside the ship, Barnard is time dilated. This means that Barnard ages more slowly, and so Gaia figures out that she's the one who's older than Barnard. But what happens if we look at this from Barnard's point of view? In Barnard's frame of reference, Gaia is the one who's moving on the Earth outside, right? This means that Barnard ages as normal, but being time dilated, Gaia is moving more slowly, and she ages more slowly. That means that in Barnard's rest frame, Barnard is older than Gaia is. So here's the paradox. When Barnard turns around and comes back, and he compares his age to Gaia, which twin is going to be older? Obviously, they can't both be older than the other twin. That's a paradox. So this presented an interesting poser, so to speak. It seems that special relativity can't be right, because we have two people, each one who is older than the other. But it turns out there is a way to resolve this paradox. There's something that we've missed that explains why we arrive at this paradox. And once we've discovered that thing that we've missed, we can explain who is older and why this effect happens. So the answer is that we can't use special relativity to describe this paradox. We have to use more complicated rules, the rules of general relativity. Why is that? Well, you can see a sort of hint over here. Remember that special relativity only works for inertial frames of reference. What's an inertial frame of reference? A frame of reference that is not accelerating. The thing is, if Barnard wants to compare his age to Gaia's age, he has to turn around. When Barnard turns around and goes from Barnard's star and changes his velocity and starts moving back to Earth, he is in a non-inertial frame of reference because he is accelerating. As he accelerates, we have to stop using the rules for special relativity and start using the rules for general relativity, which we don't know because they're not covered in Year 12. So if we look at the general theory of relativity, as Barnard is accelerating, both Barnard and Gaia observe that Barnard is traveling more slowly through time, right? That means that as he is accelerating, and as a consequence of general relativity, Barnard is noticing the world around him, including Gaia back on Earth, speeding up. Remember, this is not the time dilation of special relativity. This is a consequence of general relativity. This means that as he's moving around the star and as he begins accelerating, Barnard observes his sister growing much, much older. Once he gets out of the acceleration and moves at constant velocity back towards the Earth, Gaia is once again time dilated and moving slowly through time, except by this point she's already a lot older than Barnard. So by the time that Barnard arrives back, Barnard will figure out that he is in fact younger than Gaia. So both twins agree that as Barnard accelerates around Barnard's star, he is passing through time more slowly than Gaia. But, and I'll repeat it once more, this is not a consequence of special relativity, this is a consequence of general relativity. So, what this means is that when Barnard comes back, he's younger than his twin, who is presumably no longer a twin, because they're no longer the same age. But it's worth noting that neither twin has traveled backwards in time, right? Although they have traveled through time in different ways. Both Gaia and Barnard are only moving forwards in time, just like we're moving forwards in time at a rate of 1 second per second. The difference between them is that they're passing through at different rates, and that's why the age difference appears. When Barnard is accelerating, Barnard is traveling through time more slowly than Gaia. That means that he's traveling through time at a rate of less than 1 second per second. And so this is the reason that when he gets back to Earth, a different amount of time will pass for Barnard than for Gaia. So that's the end of the theory. We have covered and resolved the twin paradox. So let's go on to some questions. Question 1. An observer on a rocket traveling at high speed has a different perception of space and a different perception of time to someone who is moving relative to the first observer, or is stationary relative to us. So whose view is correct? Is it the stationary observer, the moving observer, both, or neither? Well, what does the principle of relativity say about this? The principle of relativity states that all inertial frames of reference are equivalent, right? That means that the fast-moving rocket and the stationary observer are both in equivalent frames of reference. So you can't say that one is better than the other. So we can't say the answer is A or B. If we say that one is correct, that means that the other one is incorrect. And because they're equivalent, they both have to be the same. So our answer is going to have to be C or D. If we say D, neither view is correct, then that implies that there is some frame of reference out there that is correct. And we just don't know what it is. Maybe it's this sort of ether that permeates the universe. But no, there is in fact no absolute frame of reference in the universe. The best answer is C, both of the above. And this is the correct answer. So in this case, we can say that both the observer's point of view and the rocket's point of view are both good and both equivalent. But if we take observations in each one, they'll end up being different. It's important to remember that neither set of measurements is right or wrong. Both sets of measurements are entirely correct in the frame of reference in which they were taken. Question 2. Barnard's star is 6 light years away from us. The travelling twin moves toward it at 80% of the speed of light. How long does it take them to reach the star, according to us? Now this is a fairly simple question because it's just, distance over velocity. Except we're given light years and a fraction of the speed of light to work with. Now this is actually pretty convenient so long as we only work in light and light years instead of working in meters and seconds. So why is this? It's because of the definition of a light year. 1 light year is equal to the speed of light times a year. Right? That means if we're moving at 0.8 c and we're traveling 6 light years, then the amount of time that it will take us to travel that distance is just given by 6 light years over 0.8 light. The light cancels out, you end up with years. This is why we often measure distances in light years in this sort of question. So we take 6 and divide it by 0.8, and we'll end up with an answer of 7.5 years. So from our point of view, that is Gaia's point of view, it takes 7.5 years for Barnard to reach his star. How many years older is he when he arrives? Now this is an interesting question. We know that clocks on board Barnard's spaceship run more slowly, right? Because he's traveling at very, very high speeds. So this 7.5 years is our TV, the time that it takes for a very, very fast-moving object to reach its destination. What we want to find is the speed in the rest frame. The rest frame time is given by t0. So we have TV, we want to find t0. We can use our equations of relativity to solve this equation using just this 0.8 c. So putting in 0.8 into our equation, we end up with an answer of 4.5 years. So Barnard is 4.5 years older when he arrives at the star. Question 3. According to the travelling twin in the paradox, which twin is older when Barnard is travelling away from the stationary twin? So this will be right at the start of the situation that's set up in the paradox. So according to Barnard, and in his rest frame, Gaia is the one who's moving, and the Earth along with her. So when he's travelling away from the stationary twin, and they started off at the same age, he notices that he's aging normally, but Gaia's clocks are running slowly, so she ages more slowly. That means that Barnard believes that Gaia is slowed down, and therefore Barnard is older and Gaia is younger. If you look at it from Gaia's point of view, she'll disagree. But because of the relativity of simultaneity, you can't really say that one is right and the other is wrong. Because when they're measuring their ages at the same time, they're measuring them simultaneously. And the concept of simultaneously won't be the same for both of them. So which twin is older when Barnard is travelling back towards the stationary twin? Now in this case, we know what the final state is going to be, right? We already know the resolution to the paradox. We have to end up with Barnard being younger and Gaia being older, right? But if Barnard is travelling at constant speed, that means Gaia is time dilated and ages more slowly. So according to the travelling twin, the twin at home must experience time dilation and age slower. But we also know that they have to end up older than the travelling twin, right? The travelling has to end up younger. So that means that when Barnard is travelling back towards Gaia, both of them will have to agree that Gaia is older than Barnard. I mean, if you really want to take this to the extreme, you can say when he is travelling back toward the stationary twin, you can interpret it as when he is only a meter away from reaching his destination. We know that in a tiny fraction of a second, as he crosses that last meter, he's going to be much younger than Gaia when they meet up. And so that will remain the same when he's just before that arrival point. Question 4. Explain how relativistic travel can be used to see what the Earth will be like 100 years from now, assuming you don't want to just sit around and wait for 100 years. Can you remember how the travelling twin travels through time? He simply passes through more slowly because he's moving at high speeds and accelerating. So, if we want to see what the Earth will be like in the future, all we need to do is slow down our own passage through time. So due to relativistic effects, if we're travelling at some ridiculously large fraction of the speed of light, then we might only age 1 year when we move through 51 years worth of travel from the Earth's point of view. Right? So from the Earth's point of view, our spaceship takes 51 years, but its passengers, us, only age 1 year. When we turn around and come back, how many years would have passed for each of us? Well, on the year back, we age another year, but according to the Earth, the trip takes another 51 years. So how many years have passed on Earth? Well, 51 plus 51, that's 102 years. But we've only aged 2 years. This means that once we get back to Earth, everyone there is 100 years older than we would have expected them to be. So this means that we can travel forward in time at different rates, so it's possible to visit the future, so to speak. However, we can't visit the past, and it means that if we're 102 years into the future, we can't ever go back to where we started. Question 5. Here we have another paradox about the theory of special relativity. This is another paradox that was proposed to Einstein to sort of refute his ideas and say that they couldn't possibly be right. Let's take a look at it. In the barn-pole paradox, sometimes called the ladder-garage paradox, a pole is moved at very high velocity, almost the speed of light, through a barn that has its front door and its back door open. Right? So it will just pass straight through without touching the barn. In the barn's rest frame, the pole is contracted and is very, very short. Right? This means that if we imagine the barn over here, then as the pole goes through, it will be very short and fit entirely inside the barn. But if we look at the pole's rest frame, then the pole will be its normal length and the barn will be contracted, right? So it's impossible to fit the pole inside the barn. So if we look at this frame of reference, in which the pole is contracted and the barn is stationary, it's possible to slam the front and back doors of the barn at the same time and trap the pole inside. But if we look at the pole's point of view, that's impossible, right? You couldn't possibly close both doors at once because the pole is never entirely inside the barn. So how do we solve this paradox? I'll give you a clue. It has to do with the relativity of simultaneity. Was that enough of a hint? Well, let's look at the answer. The paradox can be resolved by using the relativity of simultaneity. Now, in this paradox, what happens simultaneously? Well, from the barn's point of view, we close both doors, we shut them tight simultaneously, right? Thereby trapping the pole inside. But that's not going to be simultaneous in the pole's frame of reference. In the barn's rest frame, the doors are closed simultaneously, but in the pole's rest frame, the far door of the barn is closed first. This means that as it goes into the barn, the front of the pole will sort of ram into the door that's keeping it trapped in, while the back of the pole keeps moving forwards. You see, the back of the pole doesn't realize that the front of the pole has hit the barn, because the shockwave traveling back through the pole doesn't travel at the speed of light. Eventually, the back of the pole will get all the way inside the barn, squishing the pole down to a very small space, and then the back door will close. So this is how we resolve the paradox. It's not really a paradox at all, you see. So that's the end of the questions. We've covered the twin paradox. That is, a twin travels to a distant star and comes back. Is he older or younger than his twin? We've also covered the barn pole paradox, which has to do with length contraction at high velocity.